Imagine a star far more massive than our own sun reaching the end of its magnificent life. For millions of years or even billions of years it has burned with incredible fury, a beacon of light in the vast emptiness of space, but its fuel is running out. The star's immense gravity, held in check by the outward push of its nuclear furnace, finally wins the battle. In a final catastrophic collapse, the star implodes upon itself, crushing its own matter down to an infinitesimally small point of infinite density. This is the birth of a black hole. It is a region of space-time so warped, so distorted by gravity that nothing, not even light, can escape its clutches. These cosmic enigmas are the universe's ultimate prisons. They are not empty voids, but an unimaginable amount of mass packed into an impossibly small space. The boundary marking the point of no return is called the event horizon. Crossing it is a one-way trip into oblivion. What lies beyond this veil, we simply do not know. The laws of physics as we understand them break down completely. It's a place where space and time are so twisted that our human intuition fails us. For centuries, black holes were just theoretical curiosities, born from the mathematics of Einstein's mind. They were the monsters lurking in the dark equations of the cosmos. We couldn't see them directly because they swallow all light. They are the absence of everything we can detect with our traditional telescopes. It's like trying to find a black cat in a coal cellar at midnight. So how could we ever hope to prove they truly existed? Scientists had to get clever. They looked for the effects of these gravitational behemoths on their surroundings. They watched as stars were flung around by an unseen partner, their orbits betraying the presence of a massive, invisible object. They observed gas being heated to millions of degrees, dust swirling violently down into the abyss, screaming in X-rays just before it vanished forever. These were the breadcrumbs that led us to the lairs of these cosmic beasts. But these indirect observations, as compelling as they were, still left us wanting more. We were like detectives who had found fingerprints and footprints but had never seen the suspect. We knew something dark and powerful was out there, shaping the galaxies, governing the fates of stars, but we had never witnessed its most dramatic behavior firsthand. We yearned for a direct sign, an unambiguous signal from the heart of one of these gravitational monsters. We wanted to hear the sound of the universe's most extreme events. Little did we know, the cosmos was about to send us a message that had been traveling across the universe for more than 1 billion years, waiting for us to build an ear sensitive enough to hear it. Far away in a galaxy so distant its light has taken 1.3 billion years to reach us, two titans were locked in a final, deadly embrace. These were not just any black holes. One was about 29 times the mass of our sun, the other a staggering 36 times its mass. For eons they had been cosmic dance partners, orbiting each other in a graceful but ever-tightening spiral. Imagine two whirlpools in a cosmic ocean, each one a vortex of pure gravity, slowly, inexorably, drawing closer. With every orbit, they radiated away enormous amounts of energy, not as light, but as invisible ripples in the very fabric of space-time itself. As they drew nearer, their dance accelerated into a frenzy. The space around them was churned and twisted like a stormy sea. In their final moments, they were whipping around each other at nearly the speed of light, completing hundreds of orbits every second. The gravitational forces at play were simply beyond human comprehension. This wasn't just two objects bumping into each other. This was a collision of two separate regions of space-time, each one a bottomless pit of gravity, about to become one. It was an event of unimaginable violence and power. Then, in a fraction of a second, it happened. The two event horizons touched, and the two black holes merged into one. In that single cataclysmic moment, they formed a new, larger black hole about 62 times the mass of our sun. Now you might be a mathematician and say, wait a minute Neil, 29 plus 36 is 65, not 62, and you would be right. So where did the missing mass go? That missing mass, equivalent to 3 entire suns, wasn't lost. It was converted directly into pure energy. But not the kind of energy that produces a flash of light. It was converted into a blast of gravitational energy, a tsunami of ripples in space-time. This final burst of energy was the most powerful event ever witnessed by humanity. For that fleeting instant, the collision of these two black holes radiated more energy than all of the stars in all of the galaxies in the observable universe combined. It was a silent storm, a tempest not of light or sound, but of pure gravitational force, racing outwards in all directions at the speed of light. This was the universe flexing its muscles, showing us the true power hidden within the equations of gravity. This was the signal we had been waiting for, a death cry and a birth announcement all in one. To understand how we could possibly detect such an event, you have to change the way you think about the universe. Don't picture space as an empty, static stage where things happen. Instead, think of it as a dynamic, flexible fabric. Albert Einstein gave us this incredible new perspective with his theory of general relativity. He imagined a four-dimensional fabric called space-time, woven from the three dimensions of space and the one dimension of time. Everything in the universe rests upon this fabric. You and me, planets, galaxies. It's like a giant cosmic trampoline. The Earth creates a small dimple, the moon orbits it. Our sun creates a much larger dimple. All the planets are trapped in its well. A black hole creates a deep, almost bottomless pit. Gravity in this view is not some mysterious force. It is simply the curvature of space-time. Objects follow the straightest possible path. When massive objects move fast, they send out waves. These are gravitational waves. They are not waves traveling through space. They are waves of space itself. As a gravitational wave passes by, it literally stretches and squeezes space-time. Distances rhythmically increase and decrease. Imagine two bowling balls spiraling on our trampoline, sending out ripples. Gravitational waves are the cosmic equivalent. For a century, these waves were purely theoretical. Einstein himself predicted their existence, but he was convinced they would be so astonishingly faint by the time they reached Earth that we would never detect them. Einstein was a genius, but in this one instance, he underestimated human ingenuity. For decades, brilliant scientists worked to build an instrument that could do the impossible, detect the infinitesimal stretching and squeezing of space-time. The Laser Interferometer Gravitational Wave Observatory, LIGO, is not a telescope that looks for light. It is an observatory that listens for the vibrations of space-time, an ear tuned to the gravitational symphony of the cosmos. And on September 14, 2015, it heard its first note. The LIGO detectors are engineering marvels, two of them in the United States, located thousands of kilometers apart. Each consists of two perfectly straight, 4-kilometer-long tunnels arranged in an L shape. Inside, a powerful laser beam is split in two, sent down both arms reflected by perfect mirrors, then recombined. If the arms are exactly the same length, the light waves cancel. No light reaches the detector. But when a gravitational wave passes, it stretches one arm while squeezing the other, then alternates, changing the laser paths by amounts thousands of times smaller than a nucleus. That tiny mismatch lets a flicker of light appear at the detector. That flicker is the signal. It is space-time ringing like a bell. Converted to audio, the signal was a simple, rising chirp, the sound of two black holes spinning faster and faster, then a final thump as they merged into one, a whisper that had traveled for 1.3 billion years to reach us. This discovery was a monumental moment for science, a standing ovation for Albert Einstein. A century after general relativity, his equations predicted gravitational waves, how they'd be generated, propagate, and what two merging black holes should look like. When LIGO first saw the signal, it looked impossibly perfect. They feared it was just a test. Months of checking, no error, no alternative. The signal was real. A perfect match to Einstein's predictions from a 29 solar mass black hole and a 36 solar mass black hole merging. The story doesn't end with Einstein. This discovery also confirmed work by Stephen Hawking. One of Hawking's most important contributions, the area theorem, predicts that in any interaction, the total surface area of event horizons can never decrease. Sound familiar? Like the second law of thermodynamics, entropy or disorder of a closed system never decreases. The event horizon's size relates to mass. When two black holes merge, the final surface area must be greater than or equal to the sum of the two originals. From the chirp, scientists inferred the two original masses, computed their areas, and from the final mass, the new black hole's area. Would the final area be larger than the initial sum? The calculations were clear. Hawking was right. A decades-old prediction, grounded in theory and mathematics, confirmed by observation. A stunning victory for human intellect. For all of human history, we've explored with light, visible, radio, X-rays, and more. It was our one window. Light can be blocked by dust, and it cannot escape the most extreme gravity. Parts of the universe are fundamentally dark to us. Gravitational waves open a brand new window, a completely new sense. It's as if we were deaf and suddenly can hear. We can now listen to cataclysms that produce no light, events we'd otherwise never witness. And while the true value is perspective, pushing to detect the impossible advances technology that often helps daily life. Most importantly, it celebrates our relentless curiosity and collaboration. We stand at the dawn of a new age of exploration. The detection of gravitational waves is not an endpoint, it is a beginning. The first signal, GW150914, was just the opening note of a grand cosmic symphony. Since then, LIGO and Virgo have detected dozens more black hole mergers and a spectacular neutron-star collision seen across the spectrum. The future is bright, more sensitive detectors on Earth, and a space observatory called LISA, 3 spacecraft flying millions of kilometers apart, listening for low-frequency waves from supermassive black hole mergers. We'll go from hearing chirps of stellar-mass black holes to low rumbles of galactic titans. Why do we build these machines and look up? Because we want to know where we came from, what the universe is made of, and what our fate might be. Curiosity compelled Einstein and drove the LIGO scientists. It is the most powerful tool we have. So when you look at the stars, remember the silent, invisible ripples carrying stories of cosmic collisions and ancient cataclysms. Remember that we are a species that learned to listen, part of a great ongoing adventure to explore our universe and our place within it. And as long as we remain curious, as long as we keep asking questions and seeking answers, there will be no end to the discoveries we can make. The cosmos is waiting.